So we are going to now introduce the scientific method because that is the goal of this course, to help you to think critically about evidence-based ideas and predictions by using the scientific method. So this becomes a passion for me because I'm trying to defeat Facebook. And and so scientific thought is like the anti-Facebook. And that's a real passion for me. It's a way of looking at ideas and using evidence to decide if those ideas have merit, or if those ideas need a change, or if those ideas have no merit at all. It starts with observing a phenomena. And I am showing you here a pyrocumulus cloud. I also teach meteorology. Again, my background is in environmental sciences, so it fits in. This particular slide deck that I'm showing to you is something that I use in meteorology. The scientific method was invented by Persian and Iraqi scientists, Islamic scientists, in the 10th century. And we are just perfecting it and using it daily to make sure that we can move science forward. So it doesn't matter if I use this for meteorology or astronomy, but the scientific method did start with astronomy. So this all starts with observing a phenomena. When I talk about the Islamic astronomer who saw the Andromeda galaxy as a cloud in 905 AD, that person was observing a phenomena and then went on to do more research. And what that promotes is critical thinking and independent evaluation of evidence. So let's start with the steps of the scientific method in observing a phenomena like that cloud in the Andromeda galaxy, and then finding a problem with that. And there was a big problem with that, and asking why. That Andromeda galaxy didn't look like the rest of the stars in the sky. Why didn't it look like the rest of the stars in the sky? You can imagine that astronomer looking up at 905 AD and saying, why does that look differently? And then doing research. The research that we are going to talk about incorporates scientific laws, scientific theories, facts, other hypotheses from different people. We're going to talk all about these things, and then developing your own hypothesis, your own independent thinking, and then testing that hypothesis, analyzing your results, talking with your peers. And I want to show you in a circle how this goes around and around, because the scientific method is a never-ending process. So in other words, you make observations of the cloud in the sky. You think of interesting questions on why that looks differently. You come up with a prediction. Maybe that's a different thing because... And you do that as a result of things that you've researched and you found before. Then you want to go and test your prediction, but in astronomy that's very difficult to do because we can't test what is up in the atmosphere, and we can't test what is beyond our atmosphere and out into space. We'll learn about what we can do in astronomy and what we can measure in regard to our observations. You gather your data, you gather your measurements, and then you look at them and you analyze them and wonder, is my prediction correct, or do I need to alter my prediction? Do I need to expand it? Do I need to completely reject it? All of your work supports and develops theories. Let's go into that a little bit deeper. When we're doing all this critical thinking based on evidence, the point of this is to avoid sensationalism, to avoid groupthink. passion for me, to avoid groupthink, think independently, to avoid panic, to avoid wasted time and effort. I, as an EMT, saw this just months ago in COVID. Okay? And I saw the scientific method being used every day because our protocols on bringing patients into the hospital were changing literally by the hour as we were learning from the doctors inside, the pulmonologists inside, the nephrologists inside, the infectious disease specialists inside. All of this information was coming out, and it was a way to evaluate the evidence as scientifically and as quickly as we could to avoid panic, to avoid wasting time, to get to some of the mysteries about this virus that we didn't know. So the scientific method is critical to avoid groupthink and sensationalism. Now, this is a problem that that I have up here in I'm going to show this to you a little bit. This is a meteorological issue, a problem that I observed, and that many people observed. Back in January of 2020, huge fires on Kangaroo Island off the coast of Australia. This is before the fires. This is after the fires. This is all parkland on the western coast of Kangaroo Island. The parkland burned out of control and decimated the western side of this island. It killed thousands upon thousands of animals who had nowhere to go. And so I had my observation here, and I had my why question. Why did the western parkland of this island in the middle of the Indian Ocean burn? Islands are supposed to be pretty well hydrated. Why did it burn? So I had my why question. I looked around and I researched some of the theories about what happens with the Indian Ocean and with islands off the west coast of Australia, some of the theories about that, some of the facts and the data that came in, some of the other hypotheses. I know the scientific laws for the atmosphere. We'll go into scientific laws in here. And I put all this research together, and then I came up with a prediction of why this island may have burned so intensely. And then I needed to go and test that prediction. So just to back off a bit, in terms of research, you may say, well, what is the difference between a law and a theory? Very good question. A scientific law is generally describing the phenomena using equations and math, right? Two really great examples. Newton's second law of motion, force equals mass times acceleration. A mathematical description of the apple falling down from the tree. And in meteorology, we use the ideal gas law, which is a mathematical description of what happens when you blow up a balloon. Okay? So it's describing the phenomena of blowing up a balloon and then maybe letting it go and it goes darting all around the room. It's a mathematical description, pressure times volume equals number of moles of a gas times a constant times temperature. If you're in my meteorology class, you'll learn all about it. So a law, a scientific law, is a mathematical representation of a phenomena. And a theory is an explanation of the phenomena instead. So Einstein's theory of relativity explained how gravity impacts mass. It didn't concentrate on the math. It explained how this happened. In meteorology, we have a kinetic theory of gases. It explains how particles of gases move to produce air pressure. So again, the theories don't involve math. The laws do. A hypothesis is my prediction of how that could have evolved. So my prediction can lead into a theory and can support a theory. If I've got great data for my prediction, my hypothesis, it's going to support a theory. And a prediction or a hypothesis is generally structured into an if-then statement. And the if parts involve the scientific laws that are in my research, the scientific theories that are in my research, the scientific facts that are in my research. So, an example, if gravity impacts all objects and masses, and it does, to pull them toward the ground on Earth, there's gravity everywhere. Probably should change that a bit. And an apple has mass, and that's a fact. An apple has mass because an apple has matter. Then an apple can fall to the ground. So here's my if, and I can put another if here. And if an apple has mass, then an apple can fall to the ground. You might say that's not really prediction. These are very simplified. They get very, very complex. But we're simplifying it. If, and then a then statement. A scientific fact is data that is verifiable. And that brings me to another point. The beauty of science is that you can't pull any punches. You can't be an attorney and just play one side of the facts. Like the prosecutor plays one side of the facts and the defense attorney plays the other side of the facts. No, it doesn't work in science. Science has to play both sides of the facts, and they have to present them to you and let you reproduce everything that I did. So it's verifiable. So a scientific fact is verified by somebody else getting the same data or the same representation of the data. That's a fact. And that's why scientists don't really respect maybe attorneys. I'm married to an attorney, but I digress. So to create your own hypothesis, your own prediction about why that island burned, I think about my observations, I think about my research, and I think about what makes sense. And I find the very broad premises that support my explanation for things. And then I get more specific. A very broad if. Then I get more specific in my ifs. And then I create my if-then statement. So I can say, very broad, if rain can quench wildfires, duh. And if oceanic islands have frequent rain, yes. And if Australia's Kangaroo Island burned uncontrollably, which is a fact, then I predict, I'm suggesting that Kangaroo Island in January of 2020 sustained drier conditions. And you might say, duh, but you'd have to go and find out if Kangaroo Island from the data did sustain drier conditions. You can look back to all the observations that were done in the past. If you look at this right before the fire, that side of the island is quite green. It doesn't look too dry to me. So it'll be really interesting to see what the data show. And my prediction could be that dry conditions in 2021 could cause another part of Kangaroo Island to burn in 2021. This part of the island, there's no vegetation to burn. But another part of the island, maybe here, could burn. That could be my prediction. That's part of my hypothesis. My hypothesis is my if-then statement. See you on the other side.